like to briefly introduce our speaker today. That's academician Yuanpeng Li, Li Yuanpeng 院士. So about his education and training background, in 1979 he got his PhD from UC Berkeley, and then he did a postdoc at NOAA Boulder, Colorado in the USA. And after he got his PhD, 2 years later, in 1981, he joined the faculty at the National Tsinghua University as an associate professor in chemistry. And since 2004, he has become a chair professor in the Department of Applied Chemistry at National Jiao Tong University, NCTU. And between 2005 and 2008, he served as a Dean of Science at NCTU. And then about his research is mostly in spectroscopy, kinetic and dynamics of free radicals or unstable species that are important in astrochemistry, atmospheric chemistry, or combustion chemistry. And the techniques employed include a step scan, FTIR, both emission and absorption, matrix isolation with pH2, quantum cascade, laser absorption, cavity ring down, IR, VUV, photoionization, time of light detection, laser-induced fluorescence, and ultra-fast laser techniques. And then about the honors and the awards. In 1997, he became a national chair professor recognized by the Ministry of Education. And in 1999, he was elected as a fellow of the APS, the American Physical Society. And 2008, he became the academician of Academia Sinica Taiwan. And 3 years later, 2011, he was elected as a fellow of the World Academy of Science, the TWAS. And his recent awards include the Honda Fujishima Lectureship Award of Japanese Photochemistry Association in 2016, and Humboldt Research Award in 2016, and the Pimentel Prize of Matrix Isolation in 2018. And the most important, the prestigious Presidential Science Prize, 总统科学奖 in Taiwan in 2019. And today he's going to talk about some interesting developments in his research related to astrochemistry. So let's welcome academician Li.
Okay. Thank you. Thanks, Professor Wu, for the kind invitation and the kind introduction. Can you hear me?
Yes.
Okay. So today I'm going to talk about some new concept in astrochemistry and using parahydrogen matrix isolation. And I'm from National Yangming Jiao Tong University, Hsinchu, Taiwan. And first, I'll give you a brief introduction to parahydrogen matrix isolation. And then I'll go through briefly about how we make protonated and hydrogenated species. And these are related to unidentified infrared emission in astronomy. And then I will talk about the main focus today, which is hydrogen abstraction and hydrogen addition in astrochemistry. And I will talk about hydrogen abstraction and addition cycles and use the reaction of hydrogen with methylamine as an example. And then I'll talk about hydrogen-assisted isomerization and fragmentation. And I use the reaction of hydrogen with trans-N-methyl formamide, called trans-NNF, as an example. And these two experiments actually brings a new concept in astrochemistry. And first, because you are physicists, So probably you are not really familiar with the matrix isolation technique. So I'll just give you a brief introduction. And the matrix isolation technique involves diluting the sample of your interest in inner gases and then deposit onto a cold target to form a solid. However, because the concentration is very low, so the species you are interested in are surrounded by the inner gases. So in a way, it's like the species you are interested is surrounded by inner gas, and so that it's like a cage. And this was developed by late advisor Pimentel and also Professor Porter in 1954, a long time ago. And so at that time, people frequently use real gas, and that mostly argon or neon. And then sometimes people use nitrogen or oxygen as the matrix host. And the property of this matrix isolation is that in terms of spectroscopy, they are similar to the gas phase, except that there's no rotation in solid. So the spectra is simpler, so it's easier to analyze. And however, the matrix shift induced by the solid is very small, typically less than 1%. So that even though we are getting the information from the solid, but this data can be applied to the gas phase. In terms of chemistry, then it could be very different. And because of this cage effect that I mentioned, because the molecules are surrounded by inner gas. Like when you were a kid, maybe you experience the same thing. If you are very talkative, then your teacher probably would put you among all the so-called good students so that you have no one else to talk about. And so in this case, then even though if you are very active, you became inert in a way. But because of this cage effect, so when we try to photolyze a molecule, for example, nitric acid, and we try to break the NO bond, in principle, we should get OH and NO2. So if this were in the gas phase, then we should produce NO2 and OH. However, in the matrix, because the cage has a strong barrier for you to escape, so that the OH and NO2 cannot run away from the original cage. So they can only react with each other. And of course, they can form back the nitric acid. However, there are chances that the OH can attack the other side of NO2 and form HOONO. And sometimes this HOONO can even form a intramolecular hydrogen bonded species. So we were able to produce this kind of exotic species that's difficult to produce in the gas phase. One advantage of using matrix isolation is that it requires minimum amount of sample because we condense everything onto the solid. And so the species can be accumulated, and that implies that we can use isotopes and other expensive samples without too much trouble. However, because of this cage effect, to produce free radicals by photolyzing the precursor is difficult, as I mentioned before, because the radical you produce cannot be isolated well. So for the last 10 years or so, we are using a different matrix host. That's parahydrogen. Okay. You probably have learned that hydrogen has a non-zero nuclear spin, so that two hydrogen together, then the two spin can be paired either I equal to 1 or I equal to 0. And for this total nuclear spin of I equal to 1, that means the nuclear spin wave function is symmetric. Or we can say alpha alpha or beta beta or alpha beta plus beta alpha. So it's actually a triplet there. And then this wave function is symmetric. But vibration and electronic wave function are also symmetric, so that the rotational part of the wave function must be anti-symmetric to fulfill the anti-symmetric rule. So that means only Alt J is available for this kind of nuclear spin states. On the other hand, if the total nuclear spin is 0, and then it's an anti-symmetric wave function, then the rotational part of the wave function will be symmetric. That means J is even. So in other words, even though hydrogen has even and odd rotational quantum numbers, they actually belong to two different worlds. So the even J number we call parahydrogen, and that odd J number we call orthohydrogen. Typically at room temperature, then we have a mixture of para and ortho, and because of the multiplicity, so roughly it's 3 parts in ortho and 1 part in para. But if you cool down this normal hydrogen to very low temperature, then all the odd J number will drop down to J equal to 1, and all the even number will drop to J equal to 0. But the J equal to 1 cannot be converted to J equal to 0, even at low temperature, because this nuclear spin conversion is very slow, unless you add some catalyst. So to have a pure parahydrogen, then we need a catalyst to convert all the J equal to 1 to J equal to 0. And then we get more than 99.99% of parahydrogen. Why we want to do that? It's because the parahydrogen has the spherical symmetry of the rotational wave function. And so that actually this parahydrogen will have a very small molecular interaction. And as compared to the ortho, the wave functions actually has some orientations so that it's not symmetric, so that interaction is much higher. And there are many nice properties about this parahydrogen. And because it has a very small mass and then also low temperature, so the de Broglie wavelength is pretty large. So the large amplitude of 0-point vibrational motion of this lattice is maybe about 20% of the lattice constant. So that means we are not sure about the position of H2 in the lattice. In other words, the matrix is very soft. Along with this softness, then we can make high resolution spectrum because the heterogeneous interaction is small. But for chemists, the most important is then there's diminished cage effect. So in other words, originally the cage made from the inner gas is made of metal, but now the cage made of parahydrogen is like made from Teflon or some soft material, so that it's easy to escape from the original cage. So in that case, then we can easily make free radicals by either doing photolysis in situ and directly generate the radical, or we can even have photo-induced by molecular reactions So by reacting atoms or radicals with other molecules and to produce free radical. So this just shows that the two systems we have. So we need a system that cryo system that can cool down the matrix to about 3 degrees K. But then we need another one so that we can convert normal hydrogen into parahydrogen. And these two systems actually share an FTIR for the infrared detection. And you can see that in this system, we have an electron gun equipped here. So the first part I'm going to talk about is how we produce protonated species by electron bombardment. And in astronomy, there are this unidentified infrared emission, which was observed in many interstellar objects. And as you can see from these red bands here. So they are all similar, except maybe different relative intensities. And these infrared emissions are characteristic of CC double bond of aromatic hydrocarbons. So one of the hypotheses is that the emission comes from this polycyclic aromatic hydrocarbons, we call PAH. And the PAH was excited by ultraviolet excitation and then goes through inter-system crossing. And then this highly vibration excited state will quench down. And during this quenching, the infrared emission was emitted. However, so far, no species of PAH has been identified as a carrier of this UIR emission. So people start to think about other possible candidates of this carrier. So among them, one of them is protonated PAH. That means a proton attached to the PAH. The reason for this is because for this protonated PAH, it is still closed shell. And there's no entrance barrier for the protonation of PAH. PAH has a very large proton affinity, so they like to attract protons. And there's abundance of protons sourced in space. And once you form the protonated PAH, it doesn't react with hydrogen or H2. And this just shows the building block of PAH as they grow bigger and bigger. And so that this become a candidate of the UIR emission. Typically, people believe that the PAH has to be much bigger than this coronium, and so that it can survive the UV irradiation in space. However, so far, no laboratory spectra can really identify that the PAH are the carriers of the UIR emission. And the reason is, once the PAH gets bigger, it's really difficult to prepare the protonated PAH in laboratory and then obtain an infrared spectrum. And since we have a lot of hydrogen here, so we found that a very easy way to make protonated species is just by electron bombardment during matrix deposition. That means as I'm depositing PAH surrounded by parahydrogen, I just bombard the matrix with electrons. And this electron, of course, can ionize H2 to form H2 plus. And H2 plus can easily react with another H2 to form H3 plus and hydrogen. So this is a very good proton carrier. So it can transfer the proton to PAH and form the protonated PAH. And of course, the hydrogen can also react with PAH and form hydrogenated PAH. And the protonated PAH can also be neutralized with another electron and form the hydrogenated species. And for our matrix isolation, we have no mass selection. So that means after this process, then the hydrogen, the protonated PAH, hydrogenated PAH are both present, and of course, along with PAH. So in the infrared spectrum, you'll see that at least these three species are present. So how can we distinguish these three? Of course, the PAH precursors are easy because we already know their spectrum. Okay, so we want to distinguish the protonated species from the hydrogenated. So the experiment is actually easy. We can just let the matrix sit for a long time. So the students are very happy to do this kind of experiment because they just go home and sleep and wait for the results. And so after a long period in darkness, then you'll find that there are some electrons that are trapped in the matrix can still diffuse. So it neutralizes the protonated one so that it forms the hydrogenated one. Similarly, the hydrogen atom that's trapped in the matrix can also diffuse, so it can also form the hydrogenated one. And so that means after you come back the next day, you'll find that the red one, which represents the hydrogenated PAH, will increase in intensity. And then the green one, which represents the protonated one, will decrease in intensity. So we can easily distinguish these two species. Of course, if you are impatient, then you can always irradiate the matrix with UV light, which release the electron much faster. And then you can also observe the same process. The only problem, of course, you have to be careful that UV irradiation might also photolize your sample. So this just shows a earlier example to show how nice this technique is. Before our experiment, typically people use two methods to identify the protonated species. One is infrared multi-photon dissociation. That means they use intense infrared laser and then try to excite the species, the protonated species, to much higher energy so that they can kick out the hydrogen, and then so that they can observe the change in their ion signal. However, because of this intense infrared beam, so the bands they observe are typically very broad and also redshifted because of the anharmonicity that's required for the infrared multi-photon excitation. And the second method is the infrared photo detachment. Okay, so for this kind of species, then people will use argon to form a complex in the supersonic jet. So they will have a species attached with a weakly bound argon. And then they irradiate this with infrared so that they can kick out the argon and so that they can see the change. So strictly speaking, they are not observing the spectrum of this, they are observing the complex. However, because the interaction between argon and the protonate species is small, so the spectrum didn't affect much. And so this is a spectrum that's observed from this infrared photon dissociation. As you can see that now the band is narrower and then it has more structure. And this one shows the spectrum that we obtained by our electron bombardment. You can see much narrower line width and then a lot more lines could be observed. And we can compare with theoretical calculations on the predictions of these protonated species. In this case, this is the protonation on the one position. And you can see very good agreement in terms of position and relative intensity. So we can easily identify the isomer of this protonated species. And so we started to make our PAH bigger and bigger. So from pyrene, chlorine, ovalin, and these are the stick spectrum that we observed. And let's compare to the UIR emission that observed here. And as you can see that as the size increases, then this CC stretching start to have a rule shift. Okay, and that's pointing toward the right direction of the UIR band. And then this another type of CC stretching actually is redshifted. Again, it's pointing towards the right direction of UIR. And this characteristic CH2 scissoring is rule shifting. And then the in-plane CH bending doesn't change that much. And then the outer plane CH stretching is also rule shifting. And as you can see that from this increase in size, we can see actually a general trend that actually pointing towards the UIR. But of course, we are not there yet. That means we need much bigger PAH. And so if you are interested in this part of work, you are welcome to look at two perspectives that we published several years ago. They are both in physical chemistry, chemical physics. One in 2014, one in 2018. And the last one actually made the cover of this journal. And the most recent one that we did with this is quinone, which has a nitrogen in this benzene. Okay, and I skip all the details, just tell you that with electron bombardment, then the proton prefer to attach to the nitrogen here. And then also the hydrogen prefer to attach here. But with another method that I'm going to talk about later, we can produce much more efficiently hydrogen, and then we can find that hydrogen can actually attack 1, 2, 3, 4 different sites of the carbon. And the reason that we do this nitrogen-containing PAH is because people believe that with a nitrogen substitution, then this CC stretching band will have a rule shift and pointing towards 6.2. So if we compare the naphthalene without nitrogen with the quinoline that with one nitrogen, indeed you can see this rule shift. So that also indicates that maybe some of the UIR band has contribution from the nitrogen species. And I just want to show you this to tell you that we can distinguish different isomers. And as I say that because we have no mass detection, so to distinguish these different species, we need the secondary photolysis. That means we irradiate the matrix with different wavelengths of light and see how they change. So these are the different spectrum after each irradiation. So you can see that some increase in intensity, some decrease in intensity. And so by sorting out the photochemical behavior, then we were able to group all the observed lines into 5 groups: A, B, C, D, and E. And they all behave differently at different wavelengths. And so then we can compare the spectrum of group, for example, group B, with the theoretical prediction for the hydrogenation at position 3. Then you can see that the most intense one is here, which agrees here, and the rest are very small. So these are all color-coded so that you know that they agree very well. And then the green agrees with the green, and pink agrees with the pink, and the blue agrees with the blue. So that way we can distinguish all these 4 isomers of the hydrogenated species. Now I'm going to move to astrochemistry. As you know that there has been a postulate that prebiotic molecules, that they have functional groups that resemble the biogenic molecules, and they are thought to be involved in the formation of molecules that are relevant to life. And so people are interested how these molecules were formed in interstellar media. And among them, of course, one of them is the amino acid. It's amino acid. As you can see that this peptide on here. So if you look at there, then you can see that this part is actually the methylamine, and this part is formamide, and this part is glycine, and this part is acetamide, and also N-methylformate is here. And so this will be the precursors of amino acid. So we are interested in learning the reactions involving these building blocks. The astrochemistry is actually still in its infancy because we really don't know much about the real chemistry. And as you can see from this chart, which is a popular chemical model for these astrochemical reactions, okay, as you can see that hydrogen reaction plays a very important role. However, in this chart, you can see that the only type of reactions that you see here is the hydrogen addition. That means if you start from CO, then HCO, H2CO, CH3O, and methanol. So hydrogen addition one by one, and eventually converts CO into methanol. Any questions? Any problem? Okay, and so as you will find out that so this model is inadequate to describe many things we observed. And so we try to use our parahydrogen and to study the reaction of hydrogen. And there are many ways to generate hydrogen, but the most efficient way is to use UV IR irradiation of a matrix containing a small proportion of CO2 in parahydrogen. And as you can see that the chlorine molecule only needs about 365 nanometers. So it's relatively long ultraviolet light to dissociate. once the chlorine atom is dissociated, it's inert to hydrogen because first, the reaction is endothermic, and then the barrier is relatively high. So this reaction, chlorine plus H2, cannot happen to form HCl plus H. However, if we irradiate with infrared light on the matrix, then we can excite some of the H2 into the V equal to 1. And this gives you about 4180 Grimm numbers. And so this will exceed the barrier so that the reaction can proceed and form the hydrogen atom. So basically, then we use UV to produce chlorine atom, and then infrared to produce the hydrogen atom. So this is a controlled way to make hydrogen atom. Once the hydrogen is made, then it can go through the quantum tunneling. That means this hydrogen molecule doesn't have to go through all the cages because it can actually tunneling through, and so that it can break the HH bond nearby and form the new one, so that it doesn't have to physically diffuse through the matrix. It can just go through the tunneling reaction and then move around within the lattice, and eventually you'll be next door to the reactant that we are interested in, and then you'll react and form a product. So this is a very efficient way of making hydrogen reaction and without irradiation, because after IR UV irradiation, then we don't need light. So it just does the quantum tunneling. And for the last few years, we have been successful in observing the hydrogen reactions with these amino acid precursors, like formaldehyde, methyl formate, acetamide. And then we found that instead of hydrogen addition, actually hydrogen abstraction plays a very important role. So in all these cases, we found that hydrogen will be abstracted by another hydrogen atom and form the radical. And as in this case, for formamide, then we have H2NCHO. Then the first step is to break the fermion hydrogen and form H2NCO. And then the next step will be break the hydrogen on the nitrogen atom and form HNCO. And then, of course, the hydrogen can add back to these two sides and then convert it back to the original formula. So this is a dual cycle. So hydrogen abstraction, hydrogen addition, so that the HNCO and H2NCHO will form a quasi-equilibrium, so that then we can explain that why in astronomical observation, the concentration of HNCO and H2NCHO are always constant, no matter what. And it's because of this chemical link. So this is the first thing that we observe, is that actually hydrogen doesn't just add to molecules, but hydrogen can also abstract hydrogen from molecules. So now I'm going to talk about the reactions of hydrogen with methylamine. And this is important because methylamine is a precursor of glycine, which is an important precursor for amino acid. And actually just last year, Yopoulos and co-workers, they reported that they can produce glycine from a system that containing CO, methylamine, O2, and then bombarded with hydrogen atom. Then they found the production of glycine. Of course, they were only able to look at the end product, but they proposed that the reaction that producing glycine might be because they have H or OH in their system. So H or OH will abstract hydrogen and form this CH2, NH2. And CH2, NH2 will react with HOCO. HOCO, again, comes from CO plus OH. And then these two radicals will be combined and form glycine. However, in their system, they did not observe this, so they were not sure if indeed this was produced. And our system is very suitable for producing and observing this kind of radicals. So the experiment is done like this way. So we deposit methylamine and a little bit of chlorine in peroxide. And then we fertilize with 365. In this step, we are producing chlorine atoms. And then we irradiate with infrared light, and so that we can produce hydrogen atoms. And then we let it sit in darkness for 12 hours. And then during this period, hydrogen ternary reaction will take place. And then we carry out secondary photolysis to distinguish different groups of lines that we observe. So if we skipped all these details, just to tell you that after this process, we were able to identify two groups of lines called Group A and Group B. Okay. And they have different behavior in different experimental steps. And then if we compare, okay, this spectrum shows experiment that shows Group A is pointing downwards, that means it's destruction, and then Group B is formed. Okay, and then compare with theoretical predictions of the infrared spectrum of these two species, then we can easily identify that indeed Group A is due to CH2 and H2, and Group B is due to CH2 and H. And so we can also carry out the calculations in potential energy and try to see if this is reasonable. So we start with methylamine here, then we find that the first abstraction, it can be done either from the abstraction of the hydrogen on nitrogen atom or the hydrogen on the methyl, but on methyl has a lower barrier. So this is a lowest energy path. So this will be the dominant path, so that indeed then we can form CH2 and H. And then the second step is to take out the NH. And in this case, then there's no barrier. You can, because this is a radical, so that you can easily form CH2 and H. And then now you want to add back the hydrogen. So the first addition has a small barrier, and then you form back CH2 and H2. And then the second addition, again, this is to a radical, so there's no barrier. So you form back methylamine. So by going through two hydrogen attraction, two hydrogen addition, even though you form the same CH2, CH3 and H2, but actually you are converting 4 hydrogen atoms into 2 hydrogen molecules. So there's a lot of exopsomaticity associated with that. And And this is why we can do this hydrogen abstraction and hydrogen addition in darkness without any energy input. And of course, there's about 30 kilojoule per mole barrier. So that means the reaction is slow because you need to tunnel through this barrier. Okay. And so we can monitor the mixing ratio of each species. You can see the decay of methylamine and the formation of CH2 and H2. You can see this anti-correlation here. So it really shows that indeed this CH2 and H2 was produced from hydrogen abstraction. And we can do hydrogen deficient or hydrogen rich experiment to confirm that our proposed mechanism. Then we can also do deuterated experiment, by deuterating the methyl hydrogen with deuterium, and then we can observe CD2NH2, which shows the first abstraction of deuterium, and then also CD2NH, that's abstraction of NH. And then the most important here, then we observe CD2HNH2. Okay, so this isotopic scrambling, and this is because once you abstract the deuterium, then the addition is hydrogen, not deuterium, so that you actually directly prove that indeed the proposed mechanism of hydrogen addition to this radical is happening. So you observe CD2H and H2. So this is similar to what you observed before. So you have methylamine, and then hydrogen abstraction to form CH2 and H2, and then another hydrogen abstraction to form CH2 and H, and then hydrogen addition back, so that again a dual cycle form this. And this CH2 and H2, as I mentioned, is a precursor of glycine by reaction with Hopko. CH2NH was also reported to be a precursor because it can react with CO1 H2O to form glycine. So we can determine this, and because of this dual cycle equilibrium, then we check the literature and try to plot this is a log-log plot. I try to plot the column density of CH2NH and methylamine, then you can see that almost linear relationship. That means then the relative concentration of these two species are related. That's about 0.3. Okay, and this is likely because of the chemical link between these species. And so I'm going to move to the next example, the NMF, N-methyl formamide. Okay. As I mentioned, that we started formamide to form this dual cycle equilibrium, and then so we want to replace the one hydrogen with methyl. So then that's acetamide, and try to see what happened. And then in this case, for formamide, we can see the first hydrogen abstraction, second one. But for acetamide, then we can see only the first one on the methyl. Then it stopped. Okay, so we were able to observe this radical. Okay, but this reaction indicates that after this abstraction, then many different species can add to this radical so that they can change the functional group or increase the carbon length of this amino acid precursor. But now we want to see that if we replace the hydrogen on the nitrogen, and what would happen. And this NMF is the smallest molecule that observed in astronomy that has trans and cis isomers. Okay, so the trans means the NH and CO are in trans position, and cis means they are in cis position. Trans is more stable than cis. So in astronomy, we only observe trans so far. However, for other molecules like formic acid, then we will find different isomers. And sometimes the high energy isomers has more abundance than the low energy. So people were confused, what exactly happened for this kind of different concentration. So in this case, then we deposit trans NMF. Then you can see the trans and a little bit of cis here. And then again, after 365 to generate chlorine atom and then irradiation generate hydrogen, then we start to see two different groups, which will differentiate by the secondary photolysis. And these two groups can be assigned the two radicals as we color-coded. The red one, group A, corresponds to the trans radical, that attracting the formyl hydrogen, and the green one corresponding to the attraction of methyl radical. And spectroscopy, we can easily tell because of this CO double bond here, because if you grab the formyl hydrogen, then you can actually see a blue shift of the CO double bond, which was indeed observed. And then if you attract this methyl hydrogen, basically there's almost no change here. So we can clearly identify these two radicals. And attraction of the formyl is the major channel. And then again, we can look at the temporal evolution of each species. So you can see the decay of the parent. But to our surprise, we found an increase of cis NMF. Okay, so remember, cis NMF is the high energy isomer. And all this time is in darkness. So we are actually converting some of the trans NMF into a high energy isomer in darkness. Why? So we did the calculation, try to explain. And again, we start from trans NMF, then through a small barrier, and we form this radical as we observed. Then of course, another attraction forms. Another radical we also observe. However, then after this, we attract a second hydrogen, so that then this NH will be broken, so that we'll have CH3NCO. CH3NCO. And now we want to add hydrogen back. However, in this time, because nitrogen is here, so there's lone pair, so that force the hydrogen to only go to this side, like on this side. So that means then, even though I started from the trans radical here, but after CH3NCO, if I add back the hydrogen, I can only form the cis configuration. I can only form this configuration, not the trans. And since I only form the cis, then after the second hydrogen addition, then I can only form cis NMF. not trans. As you can see from here, if I want to convert trans to cis, I need to go through a large barrier, which is about 70 kilojoule more. And then this is endothermic again by maybe about 10, less than 10 kilojoule. Okay, so in darkness, there's no way we can convert the trans NMF to cis NMF. However, if we go through this process, then we can actually convert the trans to cis. So if we simplify the scheme, then you can see that I start with trans NMF, then one hydrogen abstraction, second hydrogen abstraction. Abstraction is blue, addition is red. Okay, so I form CH3 and Cl. However, the hydrogen addition is blocked here, so it can only go this way, and then form cis NMF. And of course, there's also other channels that we observe that after forming the radical, then the addition of hydrogen can actually break the CC bond and form CH2NH plus Cl or HNCO plus methane. And same thing for this radical. For the hydrogen abstraction, then we can form CH2NH and Cl. Okay, so this is again the new concept that breaking the CC bond, which needs a lot of energy, by hydrogen atom and without irradiation. Because before we always think that to break the CC bond, we need irradiation. But now with hydrogen atom, we don't need irradiation. We can break the CC bond. Okay. So if you don't understand all the details, just remember what we observe is from the trans NMF to cis NMF, it actually has to go through a big barrier and then also endothermic. So if I want to go this way, it's not possible in darkness. However, if I make use the hydrogen reaction, because H plus H forms H2 has about 480 kilojoules of exothermicity, then what I did is actually I'm bringing this system to up here with a lot of energy so that even though I cannot go uphill here, but then I have enough energy that I can go downhill here, so that I can convert the trans to cis. Okay, so this is actually very similar to our body. We always convert ATP to ADP and use the energy to make many endothermic reactions to take place. And so, in a way, hydrogen atom is like the interstellar ATP. So it actually can bring in a lot of energy and make many things happen without light. So in summary, I tried to tell you that the reaction of hydrogen is much more than we originally thought. So we can see the hydrogen abstraction, and then we can also see the conversion to hydrogen high energy isomers. And we can also see the decomposition of radical after hydrogen addition, hydrogen abstraction. So I just want to emphasize the importance of the hydrogen reactions in strong chemistry. So we need to include all these reactions in order to understand better the chemistry in interstellar media. With that, I thank you for your attention, and I thank the funding support from MOST, Minister of Education. Thank you.
Okay, great. Thank you. Right. So now is the Q&A session. So any questions from the audience? Now in the meeting room, we have nearly 100 people, and in the broadcasting room, we also have several tens of people. So for people who are in the casting room, you can raise your question by typing. And for those who are in this meeting room, you can actually just simply speak up, talking to the speaker directly. So now is the time for questions. Any questions, especially from the students?
Maybe this is too chemistry for physicists.
It's very interesting for me because it's very close to what I've been doing, and yeah, I think it's very, very, very critical. Yeah, especially the new development here. But not sure about the students here. So anyone who has a question? If you are not confident, you can raise a question in Mandarin. That's fine too, I think. No. It's also quiet in the webinar room. Oh, there's one question here. From the webinar room, it says it's a question from Kaito Takahashi. He's asking about how much do we know about the tunneling of hydrogen in your matrix? How directional is it?
Actually, the real mechanism of this tunneling reaction is still not clear. There are still many things to be learned. For example, in some of these reactions, people found that it reacts at low temperature, but not high temperature. So this is, again, against our concept of this Arrhenius behavior. But why? We don't know. For example, if I can find the slides here. Okay, I move here. If you look at this methyl formate, so we can grab this hydrogen, the formyl hydrogen. We can also grab the methyl hydrogen. But if you look at this chart, the reaction here, this is the top chart is temperature. So this is about 4 degrees. This is about 1.7 degree. So at 4 degrees, you can see that the red one, which corresponding to the graph of formyl, stopped. It didn't increase. Only until the temperature dropped to 1.7, then it increases. But for the blue one, the graphing of this methyl, it continues increase. Of course, at lower temperature, it increases a little bit more rapid. But basically, it didn't stop. Well, the same molecule, two different sites, but they have two different temperature behavior. And we don't understand why.
Okay. So any more questions? Okay, Kaito Takahashi said very interesting about this selectivity, and thank you. Yeah.
Yeah, I don't know where he typed. I couldn't see
Yeah, because he is in the webinar room. We have
Oh,
a
okay.
limitation of 100 people in this meeting room. So I'm doing the broadcasting at the same time in the webinar room. So there are also other several tens of people in the webinar room.
Okay, so
Yeah,
I cannot
yeah,
see him.
yeah, that's fine. Yeah. All right. So any more questions from the audience, especially students? Are you still recruiting students in your lab, in your
Of
group?
course.
Okay, great. So you people hear that, right? Yeah. So if you are interested in this topic involving quite high tech kind of experiments, you feel free to contact academician Lee, Li Yuanshi. I'm sure he will be very happy, to talk to you.
Yeah, we need all kinds of people, postdoctors, visiting scientists, students, anyone.
Okay, cool. Sounds cool. Yeah. Right. So I think I'm sure there are. Well, it's always like the students are having kind of a hesitation to raise questions because we mostly use English, and I think it's totally fine. Some people may write to you after the talk.
Yeah, they're
So
welcome.
yeah, so since it's been quiet for some time around here, so that's probably call it a day. So if there is no more question, then let's thank uh, Yuan Peng Yuan Shi, yeah, Academician Lee again. Thank you.
Well, thank you for your attention.
Yeah, thank you for spending time with us. It's really our great honor to have your this very very great talk. It's very interesting to me. Yeah, right. Thank you. Yeah, a
Okay,
lot of
thank you.
yeah, a lot of thumbs up I saw. Yeah, from the within a row. Yeah, right. OK,
Okay,
thank you. Yeah，
OK，
谢谢，
拜拜，
谢谢李院士了。OK，拜拜。
拜拜。
然后助教现在可能要抽点，然后有部分同学不小心使用了台大的 G System 的 email，所以会进不来。所以下次记得用 NTU Mail。然后系统我看到好像确实有部分的问题，造成少部分同学刚开始进不来。对，所以我现在就把时间先交给助教。OK，品琪。
那还是我把刚才没点到了，现在点一下，现在有点到就算有。好，陈亮宇在吗？我点到的在聊天室扣个777，然后陈亮宇、黄静言、黄子勋、黄婉婷。
陈亮宇在我这边，有一些同学他因为进不了 meeting room，所以我请他到 webinar room。陈亮宇在 webinar room 这边。
黄静言、黄子勋。
webinar room 这边有的话，也回在的这位是22059，黄婉婷也在，
好，那
黄金妍在，
那苏俊伟现在在吗？然后，吴彩颖在吗？萧守燕、林继阳，
跟我们的有差吗？
然后
吴彩颖在，吴彩颖回复在，然后萧守燕回复在，
然后林继阳，林继
林静
阳在吗？
阳好像是22026吗？
046，
有个026回在，不知道是谁。
OK，那046在吗？046在吗？
肖俊伟、苏俊伟，你有刚刚有点他吗？
有啊。
有，他说他在。
廖根义在吗？然后吴明宏、林承汉在吗？
林承汉在。
然后张佑明、陈玉瑞在吗？
好像不在。
那以上我刚才点到还没有的就缺席啦。
OK，好，那大家离开之前，就是这周好像系统问题比较多，然后有部分同学没有办法准时进来，这个我后续会清查一下，看他问题到底在哪里。那理论上应该是都有发出信，对，不过我会再做一次地毯式的清查，有可能有一些人这个真的是没有收到系统的关系，所以我想以后大概就是这样。各位在演讲的前一天啊，如果还没有收到这个演讲连接的信的话，那请你务必写信给我。我的 email 大家应该有吧？我打在对话框好了。因为基本上这些设定大概是我这边做的，所以如果你在礼拜一的时候你都还没有收到演讲的连结，那请你发个信给我，我来查一下看到底是什么原因。这次真是太奇怪了，上礼拜还蛮顺利的，这次竟然有不少，大概我这边收到可能有4、5位同学说他没有办法进来，或是有点问题，对。然后我们下一周的讲者，今天呃临时取消，然后我会再试着找找看哈，然后呃这个下周我们先暂不取消，如果下周真的要取消的话，我会通知各位好不好？我如果没有通知各位，理论上应该是这样讲啊，我在下礼拜二之前，也就是说礼拜一最晚礼拜一，我会要么寄给大家下周的演讲连结，要不然就是会通知大家取消。那目前下周的讲者他现在是今天临时取消，所以我现在赶快再来找。然后有人问说每周都有信，理论上是的，哈，每周都会有信。那最晚这个上周因为是比较赶这个学校新的政策，那这周的信应该是在4月22号的时候就已经发给大家了。对，也就是说，我再讲一遍，最晚礼拜一，如果你觉得你都没收到信，应该要收到取消或是说演讲连结的信。如果你礼拜一还是没有收到，那麻烦。